Hi, in this video we will study the relation between linear transformations and matrices. We will see how these two are related, and actually at the end of this video you will see that every linear transformation will be identified by a matrix. Okay, let us start with this easy fact that every matrix A, let's say it is M by N matrix, defines a linear transformation. While that linear transformation we will denote it by T subindex by A, it means that it depends on A. And where does that go from? So it goes from Rn to Rm. How is it defined? So we want to define what is TA at a vector v. V is coming from Rn. Well, this says that, okay, you just defined matrix multiplication of A and V. So if you look at this matrix multiplication carefully, you'll see that note that A is M by N and V is a vector, so it has N rows, one column. Then when you multiply is going to be a vector or is a matrix which has M row and one column. So that's why it goes from Rn to Rm. But you may say, why this is linear transformation? So let me maybe write this as theorem, and then we can prove this theorem. Well, to show that that is a linear transformation, what we need to check is if I fix a matrix and then do C V1 C1V1 plus C2V2, this it will give me A times C1V1 plus C2V2. This is matrix multiplication. We know that matrix multiplication works nicely with addition. So it distributes over addition. So it will have CB1 plus ACV2. Well, these are C1, C2. And then matrix multiplication and scalar multiplication are nice together. So this will be this plus C2AV2. Well, if you look at this, what we did here a little bit carefully, you notice that at the end, what we found is AV1. AV1 is TA acting on V1. And then it is multiplied by C1 plus C2 TA of V2. And that shows that this is a linear transformation. That's it. Yeah, so give me any vector, any matrix you like. I can make a linear transformation out of that. For example, if A is 2, 1, 1, 0, negative 1, 3, then TA of this is 2 by 3. So it will go from R3. So you get a vector X, Y, Z. And the resulting vector is going to be A times X, Y, Z. But we can do this matrix multiplication. 2, 1, negative 1, 1, 0, 3. You multiply it to X, Y, Z. What we get is 2x plus y minus z, and x plus 0 plus 3z. So TA in this case is, as we showed, is sending x, y, z to a vector with two components, 2x plus y minus z and x plus 3z. Well, this is nice, yes. We have tons of examples now in hand, but what is more interesting is that every linear transformation is a linear transformation of this form. By the way, these linear transformations are called matrix. So let me write definition. Linear transformation, TA, the linear transformation defined by a matrix are called matrix transformations. And what is interesting is that every linear transformation is a matrix transformation. Okay, so let me write this as the theorem. Every linear transformation, T going from Rn to Rm, is a matrix transformation. Meaning that is there exists M by N matrix A such that T is TA. So every linear transformation is defined by a matrix. How do we find that matrix? So the A is, so what you do is this. We are going from Rn to Rm. For any vector E1, you see the standard basis for Rn. You call them E1 up to En. You apply T over E1, put it in the first column. And then you apply T of E on E2. You get another vector, put it in the second column. You apply T on E3, you get another vector, put in the third column, and up to TEN, you get the last column. The matrix you get is going to be an M by N matrix, and that's the matrix we have. You may say, why is that so? So why do we have this? Because you see, every vector you find V, you can write this vector as the first component times E1 plus the second component times E2 up to nth component up times En. Yes. But T is linear. This means that we have x1 T of E1, x2 T of E2, and this goes up to xn T of En. But this is the same thing as we start with a TE1 in the first column, TE2 in the second column, up to TEN in the nth column, and multiply it to the vector x1, x2 up to xn. And that is why this is going to be A. So what do? We always find the value or the image of EIs under this transformation, put them in the column, first one in the first column, second one in the second column, and so on, and then form the matrix. That matrix is the matrix we are going to use in that form. So definition, that matrix actually has a name. The matrix A given for the linear transformation in the theorem is called, it has a name. It is the standard matrix of the transformation T. The standard matrix of the transformation. So for any linear transformation, you can assign a matrix. So let's do some examples for this. Oops. I have some examples. Okay, T goes from R2 to R2. We want to find the standard matrix. What do? Here, we find T of E1. E1 is 1, 0. And then we find T of E2, which is 0, 1. Let's see, what is T of 1, 0? So X is 1. Y is 0. This will be 1 plus 0, 3 times 1 minus 2 times 0. This is 1, 3. 0, 1. X is 0, Y is 1. So this is going to be 0 plus 1, 3 times 0 minus 2 times 1. And that is 1, negative 2. So we put this one in the first column, and this one in the second column. That is the matrix. So the standard matrix for this transformation, A, is 1, 3, T of 1, 0 in the first column, and T of 0, 1 in the second column. And you can check that actually this T is the same thing as A multiplied to X, Y. That's a good practice. You pause it and try to see if that occurs here or not. How about this one? Okay, we have three things. We need to find T of E1, 1, 0, 0. T of 0, 1, 0, E2. And T of 0, 0, 1. Here, 1, 0, 0. X is 1, Y and Z are 0. So this will be 1 minus 0 plus 2 times 0, which is 1. 0 minus 1 plus 2 times 0, this is negative 1. And 0 minus 0 plus 2 times 1, which is 2. So put these guys in the column of a matrix. Call that matrix A. So first one in the first column. Well, it is just one number, so I will put it there. Here, the second one in the second column, negative 1. The third one in the third column, 2. That's the matrix that we are looking for. In other words, this guy is going to be 1, negative 1, 2 multiplied to X, Y, Z. And you can try that. That gives you an equality. Last example. This is, we have a transformation which sends V to its reflection in a Y axis. So if it is, say, X, Y here, it sends to the reflection of that. But what does reflection in Y axis do? Well, it keeps Y the same but multiplies X by negative sign. So this is, I did for points, but for the vectors, basically T of xy is going to be equal to minus x y. So we want to find the matrix of this, the standard matrix of this. So we need to find t of 1, 0 and t of 0, 1. What is a t of 1, 0 give us? So this is negative 1, 0 and this is 0, 1. Put this in the first column. This is negative 1, 0. Put this guy in the second column, 0, 1. That's the matrix. And as you can see that t is going to be, so here this guy is equal to negative 1, 0, 0, 1 times x, y. So that's the matrix. And as you can see, we can use matrices to define linear transformations, and every linear transformation is defined by a matrix called standard matrix of that linear transformation.